have a question from that one. Okay, from the previous topic that we have studied. Correct order of covalent character. Correct order of covalent character is MCl. Okay, then M2O, then M3P, then M3PO4. Okay, the next one was M3PO4, then M3P, then M2O, then MCl. Okay, the next one is M2O, then MCl, then M3P, and then M3PO4. Okay, and this is A, this is B, this is C, and this is D. None of these. None of these. So please tell me that which is covalent character means more the covalent character, less will be the ionic, or we will say that more the covalent character means less, more the polarity, more the polarity, more the distortion of electron cloud. We will say that more will be the covalent characters. Okay, and this we have studied in the previous classes, that how the polarity depends. So can you tell me which is the correct option that we have studied? Noha, are you there?
Option B.
Option
B.
B is correct. Okay. Option B. Yes. How can you say that option B is correct? How can you say? So we are going to have M. Okay. M here is this. You can see that M3PO4 here. 3 is the valency for this one, and M is going to have 1 valency. That's why this, when you cross multiply this one, you get M3PO4, means M is going to have +1 charge. Okay, so here this 3 is from the phosphorus, not from this one. This 2 is from oxygen, not from M. So M is going to have +1, +1, +1, and +1 charge. So if M is going to have the same charge, then okay, then we will discuss that the other element that is going to have the same charge. Okay, so this is going to have -3 charge. -3 charge. This is also going to have -3 charge. This is also going to have, this is going to have -2. This is going to have -1 charge. Okay. So now you know that the product of cation and charges, those elements that is going to have much product of their charges, that is going to have much polarization power, and more will be the covalent character. Okay. So we will say that here the product of charges is 1 into 3, that is 3. Here the product of charges is also 1 into 3, that is also 3. So we are not just going to compare which one, this one or this one, which is going to have more covalent character. So after this one, we have PO4. PO4 is a polyatomic ions. Okay, so when the charges is same, like we have this 3 and 3 charges are same, both the product of the charges is same. Okay, 1 into 3 you will get 3, 1 into 3 you are going to have 3. Here it is 2. M is going to have, means here the product of the charges is 2, and then here the product of the charges is 1. So we have this one. First one will be this one, the second one will be this one, and third one will be this one. But we have to choose one of them. Which one is more, this one or this one? Which one is more? So when we have the same product of charges, then we compare the size of the cation, okay, and anion. So if the size of the anion is more, anion means anion is negatively charged. Okay, and if the size of the anion is more, so more easily it can lose the electrons. Okay, or it okay, and if the size of the cation is small, then it can attract the polar, means if we can compare here that let me explain you this. If it is positively charged particles, okay, or cation, and this is the negatively charged particle, but it is going to have, okay, so this is going to have electron. This will be more distorted if it is going to have bigger size. Why? Because if it will be far away from the center of the atom, or we can say the center of the ion, or we can say the nucleus. Okay, so more the bigger the size of the negatively charged particle, more easily electron can be distorted by positively charged particles. Okay, so here we have which is going to have more size. PO4 is going to have more size, or only P is going to have more size. So we will have that PO4 is going to have bigger size, so here distortion is easily possible. So we will say that in this the product is same, but since the PO4 is going to have much charge, bigger charge, okay, sorry, size, then this will be considered the first position, then it will be considered a second position, then this is third, this is fourth. Okay, everybody understood? That we have discussed in the previous class. Noha, we have discussed this one. Other three students have not discussed because they have not studied this topic in the previous class. Okay. So Lena and other students, Mohammad Suhail and yes, Mohammad Suhail and Lena. May I know that have you studied this topic previously? Fajan rules, the covalent character or the polarization? No. Can you please answer me this question? Have you ever studied before in class where? Because you won't be able to understood this one.
No.
No, you have not studied. Okay, Noha, you understood this one? This concept? You answer this question because that's why I'm asking. Are
No,
you having
sir.
any are you having any doubt regarding to this one?
No, sir.
That we have studied in the previous class. Okay, so dear students, we're going to have extra class or we will provide you the backup class for this one or video lecture for this one because we have studied this topic. If we again study this topic, okay, so Noha will think that why we are again studying this one, we need to complete the syllabus. So because of that, we're going to have some extra classes for you, or we will give you the video lecture regarding to this topic. Okay, so let's start the fresh topic for this chapter, that is chemical bonding, and we are studying this one. Okay, so next topic is ionic potential. Next topic is ionic potential. Ionic potential. Okay, and what is ionic potential? We represented with phi. Ionic potential is directly proportional to charge of cation, okay, upon size of cation. Okay, charge of cation. Cation is positively charged. Okay, and this size of the cation. The more the charge, we can say that more the ionic potential. Ionic potential means ionic bond. It is opposite to, we can say that to the polarization power or the covalent character. So we can say that more the size of the cation. Cation means lesser will be the ionic potential, tendency to attract the bonded pair of electrons. So why? Because if the size of the cation is greater and greater, so the outermost shell electrons will be away from this one, so the attraction power will be less. Okay, similarly, more the charge, more will be the, if the charge is more, then it will attract the bonded pair of electron towards itself, then it will consider to that it is going to have more. So we can say that ionic potential, that is ionic potential is directly proportional to charge of cation and inversely proportional to size of cation. Both is cation, both is positively charged we are talking about. Okay, understood? And why it is, when what is the use of this one? It is used to determine the polarization power of cation. Where it is used? It is used to determine, it is used to determine polarization power of cation. Okay, or we can say that degree of polarization is directly proportional to polarization power. Polarization power. Please note it down. Okay, so degree of polarization means, and we can say that polarization is directly proportional to covalent character. So more the covalent character, more will be the polarization power. Let me explain you that what is covalent character first, so that you can understand that what is a basic of this one that we have studied in the previous classes. So let me explain you. Like for example, if you are going to have a bond between the hydrogen atoms and the chlorine atom, okay, this is a positively charged ion and this is a negatively charged ion. So when they are going to make bond, in some molecules, the positively charged particle attract the electron clouds towards itself. Means there is a distortion of electron clouds take place. What is it? That for example, these electrons are making bond here, and they are going to have bond like this. They have this electron cloud is like this, electron is revolving here. But when it comes in the contact with this 7 electrons of this chlorine, the outermost seven electron of this chlorine atom, okay, because they are sharing 1 electron. Okay, 1, 2, 3, 4, 5, 6, 7. Then what actually happens? This electron clouds distort. This electron clouds distort like this. Okay, this electron cloud distorted like this. As a result, the polar, or we can say the covalent bond is formed. The covalent bond is the bond that is formed by polarization of electron clouds, or we can say distortion of electron clouds. When the electron cloud is distorted, then polarization, we can say that polarization occurs and covalent characters appears. Okay, and if there is no, we can say that if there is no distortion is taking place, then it is purely ionic compound. So ionic compound means no polarization. We can simply say that less covalent character. Okay, understood? So we can say here that we can say degree of polarization is directly proportional to polarizing power, and this is, we can say that it is directly proportional to covalent character. Please note it down. The degree of polarization is directly proportional to polarizing power is directly proportional to covalent character. We will going to discuss when we will going to discuss this one. You will understand this one, what we are studying actually. Okay. Understood? Please note it down. Lena and Suhail, done?
Yes.
Okay. And you, Noah?
Yes.
Okay. So I have told you that more the degree of polarization, more will be the covalent character. And you know that covalent character is inversely proportional to ionic character. More the covalent character is inversely proportional to ionic character. So we can say that if this is increasing, then this will automatically decreases. Okay. And you know that if polarization power increases, then covalent character increases. Okay. And we can say that if the covalent character increases, the ionic character decreases. So we can write it polarization power is directly proportional to polarization power is directly proportional to covalent character and inversely proportional to ionic character. So in general, we can say that phi is inversely proportional to ionic character. Please note it down. And then we have to move further. Done? Noted?
Yes.
So why not responding instantly? Okay, so let's move further. Now we shall be discussing the periodicity in ionic potential. Okay, so periodicity in ionic potential. What do you mean by periodicity? What do you mean by word periodicity? Repetition of something after regular interval is called periodicity. Okay, so everything that is happening along the period, okay, that we called it periodicity. Okay, or repetition of something. We know that elements we have arranged in increasing order of their atomic number and their chemical properties repeats after regular interval. So we say that this is a periodicity. Okay, the repetition of something along a period, or if a period is the element that are in the period is going to have some specific characteristics, we call them, they are showing periodicity. Okay, so because we can say that in a period, okay, charge, we know that the charge on cation increases or decreases. Tell me, charge on cation increases or decreases from left to right? In a
Increases.
period is this one, na? When you move from left to right. So this is left and this is right. Okay, the charge on period increases. Why? As you know that if I'm having sodium, that is going to have first charge, then magnesium, okay, then aluminium plus 3 charge, then carbon plus 4 charge. So we will say that the charge on cation increases as we move from left to right. Okay, and size of cation increases or decreases? Tell me. Size of cation increases or decreases? As you know that if we are having this sodium ion, it is going to have more charge, or magnesium is going to have more charge, which is going to have, which is bigger in size? Na positive or Mg2 positive? Tell me. Which is going to have more charge? Mg2 positive is going to have is a smaller charge. Why? Because this time we have in sodium, we have sodium 1 positive, we have 11 proton and 10 electrons. But in magnesium 2 positive, we have 12 proton and 10 electron. In aluminium 3 positive, we have 13 proton and 10 electrons. So since the more number of protons are attracting the same number of electrons, okay, the force of attraction will be more, that size of the atom will decrease. Okay, because here 13 protons are attracting only 10 electrons. Here 12 protons are attracting only 10 electrons. Here 11 protons are attracting, electrons are, 11 protons are attracting only 10 electrons. So here you see that the size of the size here is continuously decreasing because more number of protons are attracting the lesser number of electrons. Okay, so as we go from left to right, the size of the atom, the size of the cation decreases. Okay, got it? Understood? Understood?
Yes.
And we will say that the ionic potential also increases. Ionic potential also increases, and if the ionic potential increases, then covalent character also increases. Covalent character also increases. Okay, and if the covalent character increases, then the ionic character decreases. Then the ionic character will decreases. Okay, so if the charge increases and the size of the atom decreases, so we have discussed this one, the charge increase. Okay, so we'll say that more will be the polarization power. Okay, and the size of the atom decreases because you know that size is inversely proportional. We have written that this one, this is charge of cation upon size of cations. So size is inversely proportional to ionic potential. Okay, so we will say that more will be the ionic potential, more will be the covalent character, and less will be the ionic character. Okay, IC means ionic character. Ionic character. Ionic character. Okay, understood? This is C is covalent character. Covalent character. Okay, so if I'm writing this is sodium Na1 positive, then magnesium 2 positive, then aluminium 3 positive, then carbon 4 positive. Okay, then after silicon 4 positive. Okay, then phosphorus 5 positive. Okay, and then after is 6 sulfur 6 positive, and chlorine 7 positive. It is donating 7 electrons. Okay, they are going to have, all of them are going to have 10 electron in their outer motion. This is going to have 10, this is going to have 10, this is going to have 10, this is going to have 10. Then silicon, okay, no, carbon is not going to have 10. It is going to have, when it loses 4, we don't write here carbon, don't write carbon. The silicon lose 4 electrons, then it is going to have, this is the first, okay. This is the second period, sorry, third period. Okay, so here we have, so here we say that this is more ionic, and okay, sodium, we will say that here, if we go from left to right, the covalent character increases because as the charge is increasing and the size is decreasing. So ionic potential will increase, and if the ionic potential increases, covalent character will increases. So you know that this sodium form ionic compound, then magnesium form ionic compound, aluminium almost form ionic and covalent both, and this silicon is going to form covalent compound. This is covalent compound, this is form covalent compound, this form covalent compound. So you know that if we are moving from left to right, the covalent character increases. Okay. Okay, understood? Understood?
Yes.
Yes.
Moving to the next part here, if we have in a group, now we are moving from top to bottom in a group. Okay, so in a group, you know that size of the atoms increases, but the charge remain constant. Okay, if we are coming from top to bottom, then we know that charge on cation, charge on cation remain same. Okay, or you know that if I am having sodium, lithium positive, sodium positive, potassium positive, okay, so these are going to have same charge, but their sizes are increasing. Their size are increasing. Okay, and if the size increases, we know that covalent character is favorable with when small size is there, and there is a small size. If we are moving from left to right, the size was decreasing. So if the size decreases, we will say that more covalent character will be there. But here, if we are moving from top to bottom, because of an extra shell, here it is going to have 2 electron, it is going to have 2,8, it is going to have 2, 8, 8 electronic configuration, and the next one is going to have 2, 8, 18, 8 electronic configuration. So since as we are moving from top to bottom, the size of the atom is increasing. And if the size of the atom increases, then less attraction power will be there. You know that if this is the lithium ion, okay, and then this is a sodium ion, this is going to have Na positive 2, 8 electrons are there. Okay, so as we move away from the positively charged nucleus, the distortion power, let me explain you what is covalent character. Covalent character is that if there is a bond between two atoms, and if the positively charged particle, positively charged ion, that is called cation, it has a power to attract the negatively charged anions, electrons towards itself. Means it has a distortion power that it can attract the bonded pair of electron towards itself. It can distort the electron cloud. So if it has the capability to distort, then it is called covalent compound. It is called, then it is, we know that it is creating the poles, and poles means polarization. Means if, okay, polarization means polarization will be, if there is more polarization, more will be the covalent character. Or we can simply say if it is distorting the electron cloud. For example, if this is a cloud of a negatively charged ion and this is a cloud of a positively charged ion. So if this Na has less tendency, okay, if in place of this one sodium, if I just kept the potassium ion, which is bigger in size, so here in this one, in sodium, the nucleus is nearer, so it can attract the bonded pair of electron or electron cloud of fluorine towards itself. But if we are increasing the size of this one, if we are having K positive here, then it will not, the outermost shell will be away from the nucleus. Here it is away from the nucleus, it is far away, and it is not going to attract the to that power. Okay, so we will simply say here that distortion of electron clouds will decreases as the size of the positively charged ion increases. So mark my point, we are just talking size of the positively charged. Okay, okay, if the size of the positively charged ion increases, then we can simply say that there will be less distortion will be found there, and if there is the less distortion, we will say that more will be the, less will be the covalent character and more will be the ionic character. So if I talk about that charge on cation will remain same, so what does it means? Charge of cations remain same. What does it means? It means that along the, as we move from top to bottom, the charge remains same, but size of cation increases. increases. And if the size of the cation increases, then there will be less distortion, and we will say that less covalent character. And if there is less covalent character, we will, opposite of covalent is ionic, so there will be more ionic character. Okay, so we will say that there will be less ionic potential. Ionic potential will be less. And if there is less ionic potential, we will say there will be less covalent character. And if we have less covalent character, we will say that more will be the ionic character. So if I say that which is going to form more covalent compound, lithium chloride, sodium chloride, or potassium chloride. So you know the smallest in size, it is more covalent. And which is going to form more ionic? The opposite of this one is ionic. This is ionic. This is going to form more ionic. Okay, understood? Understood?
Yes.
And what are the applications of ionic potentials? Let me explain you. Okay. So if I simply ask you that if I'm going to have this one, this is beryllium oxide, then the next one is magnesium oxide, and next one is calcium oxide, which is going to have more covalent character. Which is going to have more covalent character? Tell me. Which is going to have more covalent character? You know, beryllium, magnesium, and calcium. These are our two positively charged. But the size of this one is 288. This is going to have 28, and this is going to have only 2. Which form more covalent? Which is more covalent? Tell me.
Beryllium.
Beryllium. This BeO compound will be more covalent because it is going to have a small size, then magnesium, and then calcium oxide. Okay, understood everybody? Everybody understood?
Yes.
Now what is the application? Application of ionic potential. What is the application of ionic potential? So we can say that ionic potentials, that means it decides the chemical behavior of the oxides, means it helps in identifying that what type of property this oxide is or metal oxide is going to form. Okay, so if we say that, if we simply say that the chemical behavior of oxides depends here we can say that depends upon the value of phi. Okay, so if we have root phi, and that is going to have value 3.2, another one is phi, and if it is going to have, means if we have value of phi which is greater than 3.2, okay, and if it is less than 2.2, and if it is exactly or approximately the value of phi, means in under root, okay, if it is greater than 2.2 and lesser or equal to 3.2, so we can have different values. So if the value of phi is greater than 3.2, the nature of oxide will be acidic. You know that metal oxides are basic in nature. But if it is greater than 3.2, then it is acidic in nature. Some metal oxides show acidic behavior, and they are called amphoteric oxides. Okay. And if the value of phi is less than 2.2, okay, then it will be, nature of oxide will be basic in nature. Okay. So we can, nature of oxide is basic. And if it is, we can say that if the nature of oxide lie between, means it is greater than 2.2 and lesser than 3.2, then it is amphoteric. Then it is amphoteric in nature. Okay. Got it? Please note it down. Done?
Yes.
Lena, are you getting this one?
Yes.
And you, Suhail, are you there?
Yes, sir.
Are you getting this one?
Yes, sir.
Okay. Now, if I ask you the simple question here, which of the following is species? Which of the following species has highest covalent character? One is boron, the next one is aluminium, then gallium, and then tellurium. Which is going to have, and these are in the same group. These are in the same group. Okay. So which is going to have more covalent character? Tell me.
Beryllium.
Beryllium. This is not beryllium. This is boron. Boron, aluminium, gallium, and thallium. You know that if the covalent character, so you know that B boron form 3 positive, this form Al 3 positive, gallium also form 3 positive, and this tellurium also form 3 positive. Okay. Okay. So if I talk about this one, so you know that this is going to have very small in size. So I'm going to repeat you again and again that smaller the size, more will be the covalent character, more will be the ionic potential, and less will be the ionic character. Okay. So this is going to have smallest size. And if it is going to have a smallest size, then it will going to have more covalent character, Okay. And opposite to covalent is ionic. So if I simply ask you another question, okay, then what should be your answer for this question? So if I ask a question that if the ionic potential of an oxide is 4, okay, then nature of oxide will be A, acidic, B, basic, C, neutral, D, amphoteric. Tell me. If the ionic potential of an oxide is 4, and if the value of phi is 4, then will it be basic? Tell me.
It will be acidic.
It will be acidic. Why?
Because it's more than 3.2.
No, that was written under root phi. Okay, that is under root phi. So the value of, if it is 4, then the value of under root phi is 2. Okay, and if it is 2, so 2 means less than 2.2, it is basic in nature. Okay, understood?
Yes.
Okay. So let's move towards the next. Everybody noted this one? Everybody noted? Should I move forward?
Yes, sir.
Yes, we were studying, I remember that we were studying the covalent bond. So let's start studying the covalent bond next topic. Covalent bond. You know that the covalent bond is the bond that is formed by sharing of electrons, and that we have written in the previous class. Noah, you have written this one. Okay. So covalent bond, let me explain you that covalent bond is that bond that is formed by sharing of electron. For example, if I'm having this structure of H2NO2, okay, then we can have this one N. We can have this structure, covalent bond, that this is a covalent bond is formed between these. How? Let me explain you. That you know that hydrogen is going to have only one electron in its outermost shell. Oxygen has an electronic configuration of 2,6. So it is going to have, okay, 6 electron here, 1, 2, 3, 4, 5, 6. And nitrogen is going to have electronic configuration that is 2,5. So it is going to have 5 electron in its outermost shell. Okay, 2 here and 1 here. And oxygen again 6 electrons. Okay, so they are why covalent bond is formed in a bond is formed in order to complete the octet. Okay, in order to complete the octet. So if I'm having this and some elements like hydrogen, okay, they used to complete their duplet. So some elements complete their duplet, otherwise all elements other than this one are going to complete their octet. So for this they are just making bond. So you know that this is oxygen atom, this is nitrogen atoms, they are just connected, so they will going to make bond like this. Okay, and this is going to make bond with like this. Okay, and similarly this is going to make bond. So every element is going to have 8 electrons in its outermost shell. 2, 2, 4, 4, 4, 8. Again 4 here, 4 here, and 4 here. This is 8. Then again 2, 2, 2, 2, 8. And hydrogen is going to complete its duplet. So the elements are going to complete its octet by sharing their bonds. This is called covalent bond, and this is sharing bond. Here the hydrogen, a bond between hydrogen and oxygen is single bond. Again this oxygen is making single bond with this one, but here it is double bond. Okay, got it? Got it?
Yes.
The similar type of bond between this is called coordinate bond, and we called it dative bond. Okay, so covalent bond is that bond that is formed by sharing of electrons. Okay, now here we're going to have the similar type of bond that is called coordinate bond. Coordinate bond, and that is also called dative bond, or we called it dative bond. Okay, or we called it semi-polar bonds, or we called it semi-polar bond. Semi-polar bond. Okay, what is this? In this, an element, an atom can use its own electron in order to make a bond. Okay, only a single element can donate its electron to make a bond. Okay, let me explain you how it is possible. For example, if I'm having this water molecule, okay, this is a water molecule. Okay, here these are the 2 electrons of, and one electron of oxygen and hydrogen is participating here. So this is the hydrogen electron, this is an oxygen electron, this is oxygen, this is hydrogen, and they have made single bond here, they have made single bond here, but the oxygen is going to complete its octet like this way. Okay, since oxygen cannot accommodate more than 8 electron in its outermost shell. Okay, why it cannot accommodate, we're going to discuss, because of d orbital is not there. What is d orbital? We're going to discuss it later. First of all, let me explain you that here the oxygen is going to complete its octet, and hydrogen is going to complete its octet, sorry, duplet, and this is going to complete its octet. Oxygen is going to complete its octet. Now oxygen cannot accommodate more than 8 electron in its outermost shell, but if an ion is there, and like there is an H positive ion is coming, which is H positive means an hydrogen atom without an electron. If it is having an electron, then it means hydrogen atom. But if it, when it loses its electron, then it is only hydrogen ion, and that is going to have only, we can say the proton of hydrogen is called H plus ion. because when it loses one of its electron, then it forms H positive. So if an H positive ions comes and attract this one, is attracted with this electron cloud, which we call lone pair. So here this is going to have lone pair. This is hydrogen, and this is another lone pair. Okay. So these are the having 2 electrons. This is also going to have 2 electrons. So when there is an attacking power, there is an H plus ion is coming here. Then these two, because H does not have electrons, H plus ion does not have electron, it has already donated. So since it is not going to have any electrons, these 2 electrons of oxygen is going, if it is going to have electron, then it is not going to make bond, because if it is going to have one electron, then it will not share its electron with this one. Why? Because it cannot have 9 electrons. Oxygen atom cannot have 9. So in order to have 8 electrons in its outermost shell, oxygen uses its own electrons and can make bond with H positive ion. Like this is H positive ion. So it can make bond with this one and can use its electrons to make bond, these 2 electrons to make bond. So these 2 electrons of oxygen, which is of oxygen only, they are used here. Okay. And when this electron is donated to this one, its positive charge will remove. But since oxygen has given 1 electron to this into this orbit and making or given one of its electron to this hydrogen ions, it was H positive, so its charge will be removed. But since it has donated this one, so it O is going to have positive charge. So this will form H3O positive ion. H3O positive ion. Okay, O positive. This is called hydronium ion. This is called H3O positive. This is called hydronium ion. Okay, so here we can say that. Okay, so this is called hydronium ion, and this is going to form the coordinate bond. Okay, this type of bond is called coordinate bond, in which the single atom is donating its electron. It's using its own electron. It is not sharing its electron. This type of bond is called coordinate bond. Okay, you understood? Understood? No, huh? Here the hydrogen ion does not have, but here this is a purely coordinate bond, because because here 1 hydrogen atoms and 1 oxygen atoms electrons are participating. Here this is coordinate bond because here 1 oxygen and 1 hydrogen atom is participating. But H plus ion does not have any electron because it has already donated, and oxygen is using both of its electron to make the bond, because single bond is made by 2 electrons. So here oxygen, since it has an extra electron, so unbonded electron, so it can use its electron to make bonds. Okay, so understood?
Yes.
So let's move further, dear students. So let's write the definition of coordinate bond. Coordinate bond. Okay, we can say that the chemical bond, which is formed by the unequal unequal sharing of electrons between two or more than two similar or different non-metal atoms is called coordinate bond. Please note it down. Now, if we are having ozone structure O3, okay, you know that ozone cannot have more than 8 electrons in its outermost shell. Some elements can have, like sulfur can have more than 8 electrons, phosphorus can have more than 8 electrons, but the elements that are in the second period of the periodic table, like we have magnesium, sodium, magnesium, okay, aluminium, silicon, not this is on the third period. So if we're talking about beryllium, boron, carbon, nitrogen, oxygen, and fluorine, these elements cannot have more than 8 electrons, especially if I'm talking about nitrogen, oxygen, and fluorine. They cannot have more than 8 electrons in their outermost shell. And there is a reason why they cannot have more than 8 electrons. So we'll discuss it later. But the elements that are below this one, like we have silicon, phosphorus, okay, sulfur, chlorine, they can have more than 8 electrons in their outermost shell. If it is possible, then they can have. Generally, sulfur have more than 8 electrons, phosphorus have, and why they have, we will discuss it later. But the elements that are of the second group, second period, are not going to have more than 8 electrons in their outermost shell. Understood? Okay. So they make coordinate bond. For example, if I'm having this ozone, okay, O3, how they make the bond? How the ozone or O3 electrons, O3 molecule is possible. For example, if I'm having this oxygen atoms, okay, the other two oxygen atoms, they are going to have 6 electrons. That is very simple, that they are going to make like bond like this one and this one. And there is CO2, sorry, there is only O2, and there is a double bond between them. And we can say that this is purely coordinate bond. Covalent bond. Covalent bond. Okay, this is called covalent bond. But what happened in O3? How the atoms are going to arrange? So if you have this structure like this, 1, 2, 1, 2, and 1, 2. So they, okay, like 6, and like 6. So they cannot make bond like this. Okay, we can say that here, if it is going to have 6, it is also going to have 6, and they started sharing. So it is not possible. The middle one will going to have more than 8 electrons, because it is sharing from this one and this one also. So it is not possible to have double bond sharing between the O. So what does they do? If they make two double bond sharing like this, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So if it may start making like this bond, like this, then these two atoms are going to have outermost shell completed, but this one is going to have more than 8 electrons. It is going to have 10, 4 from this one, 8 from this one, 8 from this one, and 2 from this one. So here is an expanded octet tool is going to, means oxygen cannot have more than 8 electrons. There is a reason why it cannot have, but oxygen cannot have more than 8 electrons. So how O3 ozone molecule, we can simply say that ozone is going to make bond, or how O3 molecule is, there is a stable structure of ozone molecule. So let's have this O. Okay, you understood? And let's have this, there are the 2 bonds. Okay, there's a double bond. This is the 6 electrons, 1, 2, and 3, 4, 5, 6. Okay, but here this is the 2. Okay, again this is going to have 6, 1, 2, 3, 4, 5, 6, and this is going to have 6. Okay, let me explain you one more time. Let me make this electron with red color of the center atom. Okay, these are the 6 electrons. 6 electrons. Okay, so here you will notice that this 6 electrons of this one is this one, and here a coordinate bond will be formed, because here this central atom, here it is going to make 8. Here this has participated the 2 electron with the central atoms, and it is going to have 8 electrons. Okay, now if it is going to make any, now it is this element is also going to have 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is an oxygen molecule. Let me make an oxygen molecule like this: 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay. Now this is an oxygen atom like this. Okay. And like this. But this lone pair of oxygen, this electron cloud, which is going to have two electrons, This is the clouds. Why we call them cloud? Because these electrons are not like this, like two particles. No, it is not particles. They are just revolving. So they form a cloud-like structure. Okay, because like the fan blades when move, they form a cloud-like structure. So here is when they are revolving. So they are going to form a cloud-like structure. So they are going to have, we called it lone pair. The two electrons togetherly, they are called lone pair. Okay. So the one of the lone pair, only the maximum bond or the number of electrons that an atoms can share as a lone pair, it is only two electrons or one lone pair. It cannot make here one here, one here. No, it is not possible. So here is another oxygen atoms, 1, 2, 3, 4, 5, 6. So this electron, this lone pair, this one, these two electrons are going to make a single bond, here like this. Okay, and we donate it with this arrow. Okay, this is the donating one. So, and it is accepting one. So accepting one, the arrow will be moved from. So here it is donating. So this will be going to have tail, and it is accepting. So it is going to have arrow. So it is represented with an arrow. Okay. Now there is a code. Now these two electrons, which are of this oxygen only, is being shared to this one, and hence it completed its octet. So let me explain you that how it is going to form one more time. So this is an oxygen atom, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 5, 6. Okay. And here it is going to have 1, 2, 3, 4, 5, 6. And there are the 4 only, and we are just drawing 1 and 1 here. Okay. So this oxygen, the central atom of oxygen, is using its own electron to make bond with this one. And now it is going to have 8. This is going to have 8 like this way. And this is also going to have 8. But here is one thing. Since the electron that is donating one of its electron to this one, because we are not using the electron of this one, it is going to have positive 1 charge, and this ion is going to have negative 1 charge. So we can have bond like this. Single oxygen atom, single bond, that is a coordinate bond. And here is a covalent bond between two here. And this is going to have negative charge, and this is going to have positive charge. This is the structure of O3. Okay. Understood? And here the electron that are being used here is of only this one. Okay, understood? The electron of this one is not participating, of this atom is not participating. This is already 6 here. Okay, got it? It is going to have 2 electrons here. It is going to have 1, 2, 3, 4. So please draw the structure of ozone. Noha, you understood this one?
Yes.
Lena and Suhail,
Yes.
understood this one?
Yes.
So what is the purpose of this one? That if the element does not have its own electrons, or if the central atom, if it's accept the, means if it make the coordinate bond, then its octet will be, means there is an expansion in octet rule. So the central atom electrons give its lone pair to the other ions so that it can make bond. We called it lone pair, or we called it, this type of bond is called coordinate bond. Okay. Like we have another example. Like we have you drawn this one?
Yes.
Like we have NH4 positive. NH4 positive. Similar is for NH4. Like this is nitrogen. I have told you that oxygen, nitrogen, and fluorine cannot, these are most electronegative element, and they cannot have more than 8 electrons. But since they are most electronegative element, they are just attracting the bonded pair of other electrons, and they are so much electronegative that they want to make bond. They want to attract the positively charged particle towards itself. So it is NH3, it is very happy. Okay. Here the 1 electron of nitrogen and 1 electron of hydrogen is participating. Okay, this is participating, and this is still happy. This is still happy. Nitrogen is going to have 2,5 electronic configuration. So it is an electron cloud. But when an H positive ions come, so this lone pair will attract this one and will make NH4 by using a coordinate bond. And it is so these two electrons, which was of only nitrogen, since this is H positive, so a nitrogen make bond with its own electrons. Okay, got it? And this is positively charged. This will become positively charged. Okay, understood? Note it. Done this one.
Yes.
Moving to the next one. Hydronium ion, like we have in BF3, NH3 molecule. They are just making, this is NH3 and this is BF3. Okay, they just combine together. Boron is going to have 3 electronic configuration. Okay, and this is NH3. Okay, this is going to have a nitrogen. Here is going to have 2,5 electronic configuration. And if it is NH3, okay, so this is H, and this is H. So here are the 2 electrons of nitrogen, and this is boron, this is fluorine, this is fluorine, and this is fluorine. Since these are very electronegative ions, so they are attracting the bonded pair of electron towards itself. So it is becomes slightly positive. Why? Because it is attracting, because fluorine is very electronegative. So it will be attracting the boron electron towards itself. So this electron cloud will be distorted towards this, towards fluorine. It is attracting. So it will become slightly positive. We call it slightly positive. So, and you know that this boron is going to have 1, 2, 3, 4, 5, 6 electron only. It is not, the octet is not completed of boron. So what will do, it will do, it will make a coordinate bond like this with using the only nitrogen electrons. Okay. So here the coordinate bond will be formed between these two with the help of nitrogen electrons. Okay. And there is a bond. So there is this NH3 dot BF3 type of molecule is formed like this way. Okay. Understood? Understood?
Yes.
Yes.
Similar is for NO2 and N2O4. These are important. Let me explain you that this is N2O4 and NO2 and sorry, N2O4 and N2O. So if we are having N2O, this is simple nitrogen. This is making triple bond with the nitrogen, but here is a 2 electrons of nitrogen. Okay, and here is also 2 electrons of nitrogen. So this is the 6 electrons of nitrogen, oxygen, sorry. Okay, and if 1, 2, 3, 4, 5, 6, 7, 8, the nitrogen has already completed 8 electrons here. But what will it do? It will use its 2 electrons like this one. It will use these 2 electrons, okay, to make the coordinate bond. Because if it share like this, if it starts sharing like this, so there is 1, 2, 3, 4, 5. 5 bonds nitrogen cannot make. It can make maximum 3 bonds, and here the 4th bond will be formed by using these 2 electrons only. Okay, so these 2 electrons will be used here, all for only nitrogen. So this is 6 already of oxygen and 2 for shared here. Oh, this is of only nitrogen. So it is going to have 8. It is also going to have 8, and then it is also going to have 8. Okay. Understood. And since it is donating, it is going to have positive charge. This is accepting, it is going to have negative charge. Got it? Similar is for N2O4. There is nitrogen. Nitrogen. 1 single bond between nitrogen, 2 oxygen. With this oxygen. So this is N2O2. This is 2 nitrogen atom with single bond. Every nitrogen atom has participated its 3 electrons, 1, 2, 3, and 2 are already present here. So it is going to have 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and similarly 1, 2, 3, 4, 5, 6, 7, 8. It is also going to have 8 like this. But this nitrogen, this lone pair of nitrogen is going to make bond, by using of its 2 electron with this oxygen atom. And this nitrogen atom is also going to make bond. It is nitrogen 2 electrons. These 2 electrons are going to make bond, coordinate bond with this. So since it is going, it will become minus, here it will become positive, here it will become positive. Okay, so this is N2O4 structure. Please note it down. Done. Noha, Lina, and Suhail. Are you there? Your voice is not audible to me. Speak something. Noha,
Yes, sir.
done? You understood this one?
Yes.
So let's move further. Like we have the structure of SO3. Okay. The if this is there are 2 concepts. The old concept of the old structure of SO3 was like this: 2 bond with this one, with this sulfur, and 1 coordinate bond, and here 1 coordinate bond. Okay. Okay. So here the sulfur is going to have 2,6 electronic configuration. 2 are shared here, but it is going to have 2 lone pairs, 1 lone pair here, 1 lone pair here. So this is an old structure, old. Okay. And we know that in modern, an atom can share maximum 1 lone pair. Okay, it cannot share 2 lone pair. Here, single atom of sulfur is sharing 2 lone pair. Means 2 pair of electrons. 1 pair here, 1 pair here, which is not practically possible. So its modern structure is as this one. Now you can say that here the sulfur can make 1, 2, 3, 4, 5, 6. Means 12 electrons are there in the outermost shell. The sulfur can have more than 12, more than 8 electrons in its outermost shell, because it belongs to the 3rd period. And what is that specialty in 3rd period? We're going to discuss this one when we'll study periodic classification of elements. Okay, so here we say that if the question comes in examination that the number of coordinate bond in SO3. So if it is only means 0, 2, 3, 4, and 1 is given. Let me explain you. Have you noted this one? Have you made this one? Have you drawn? Tell me, have you drawn? No, huh? Suhail, done?
Yes, sir.
Yes, sir.
Okay, now the question comes, if the question comes that SO3, that SO3, okay, how many coordinate bonds are present in, how many any coordinate bonds are present in SO3. So if the question comes that it is 0, second one is 2, third one is 3, and the fourth one is 1. Okay, so since it is saying 0, and in the modern technique we have this 0, so there is no coordinate bond. Okay, so we'll take 0, okay, and the option may 0 is not given in option if 0 is not given. So this is according to modern, okay, and if there is 0 is given, then we'll give preference to 0 because it is according to the modern. But if 0 is option is not given, 1, second is 2, and third is 3, and the fourth one is 4. Okay, so here 0 option is not given because in modern we have 0. Then we will take the odd one. Okay, the ancient, or we can say that the previous one, or we can say the old structure of SO3, that is going to have 2 coordinate bonds, that is going to have 2. So we'll take 2. So if there is 0, then we take 0. If the option, if in the option, if it is 0 is given, then we'll take 0. Otherwise, if it 0 is not given, then we will take 2. Okay, understood? Understood?
Yes.
Next one is covalency. What is covalency? What is covalency? The number of electrons that can then an atom can participate in bonding is called its covalency. Okay. Okay. So if I talk about what is covalency, we can say number of bond, either we can say the either it is covalent, or coordinate, okay, it can be anyone. The number of bond formed by an atom is known as its covalency. Okay, please note it down. We can say that covalency is equals to number of bond okay, and how many unpaired number of electrons are present in an atom. We can say that covalency, or the number of bonds formed by an atom, will depends on how many unpaired electrons it have. Okay, so we can say that number of bond formed by an atoms, okay, formed by an atom depends upon the number of unpaired electrons. Okay, the number of bond is equals to number of unpaired electrons. Please note it down. And that is also equals to covalency. Done?
Yes.
Okay, so if I'm having beryllium, the electronic configuration of beryllium is 1:2. The electronic configuration is 2, 3. Okay, sorry, beryllium, that is 2, 1s2 and 2s2. That is going to have 2, 2 electronic configuration. So 1s2, okay, and 2s2. So this is the first shell, and then the second shell, it is also going to have 2 electrons. Okay. Now this s orbital, we can say that in the ground state, it is going to have this. This is the field. This is the first shell. We don't write the first shell electronic configuration. We always write this the outermost shell, and this is the outermost shell. I'm just writing here just to explain you that this is the 1s2 and this is 2s2. Have you studied the structure of atom? And have you studied this electronic configuration? Abdul, sorry, Lina and Noha. Have you studied the
Yes.
electron? And you, Lina and Suhail,
Yes.
you have studied? Okay.
Yes.
This is electronic configuration. This is 1s2 and this is 2s2. So it is not going to have any unpaired electrons. So we can say that covalency here is 0. Okay, of this one. But when the next one is p orbital for this one, p orbital is vacant here. But when we can say that if it is beryllium is going in the ground state, okay, sorry, in the excited state. So in the excited state, this electron will jump into this p orbit. Okay, this is 1s2, this is 2s2, and this is 2p orbital. 2p is going to have 0 here. So we are just going to have 2s1. This electron will jump here. So this will become 2s1 and 2p1. Okay, in the excited state, it is going to have 1 electron here. It will jump from this one. That is 2p1. Okay, so we can say that here the 2 unpaired electrons are there. So we can say, hey, here the covalency is 2. Okay, covalency is 2. Okay, understood? Understood? Similar for nitrogen. What is the covalency of nitrogen? Tell me. Nitrogen is going to have electronic configuration 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. Okay. So in the ground state, it is going to have 2s2 and 2p3. So it is completely filled. This is 1, 2, okay, and 3. So this is unpaired electrons are there. 3 unpaired electrons. So we can say 3 unpaired electrons. And that is going to have covalency is equals to 3. Understood? So nitrogen do not have any excited state. Okay, it cannot do any further shuffling. Okay. Understood?
Yes.
Yes, sir.
Now, if I'm talking about the sulfur is going to have electronic configuration. It is going to have atomic number 16. It is going to have atomic number 16, 1s2, 2s2, 2p6, 3s2, 3p4. Okay. Now, this is the outermost shell. It is going to have completely filled and 4 electrons here. 1, 2, 3, and 4. These are 2 unpaired, 2 unpaired. So its covalency will be 2. In the first excited state, sulfur, here d orbital is also there. But this is going to have 0 electron. 1, 2, 3, 4. Okay. So this is the reason why sulfur can have more than 8 electrons in their outermost shell, because it has d orbital. While the second shell don't have d orbital. Third shell has d orbital. So since the third shell has d orbital, so the further shifting is possible here. So here this electron will jump to this one in the first excited state and will become, here is 3 unpaired electrons, 1, 2, 3. And since this D is also going to have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6. 1, 2, 3, 4. Okay. So when these electrons from this one jump to this orbit, it is going to have 1 unpaired electron. So now this and this paired electrons have become unpaired here and here also. So we'll have 5. So here covalency is 5. Okay. Sulfur is showing covalency 5. Okay. Now, if this electron also jump to this one in the second excited state, this electron will also jump to this one, and it is going to have 1, 2. So here it is also unpaired, and then this is, it is also going to have 2. Now this electron from here also jump to this one, and now it is going to have 1 unpaired here, 3 unpaired here, and 2 unpaired here. It is going to have 6. So we say covalency is 6. Okay. And number of bond formed will be 6. So we can say that sulfur can have 2 types of covalency. Understood? Got it?
Yes.
Okay. So there are so many other electrons that can have different types of covalency, and they can show in different excited state. They can show different types of covalency. Okay. Now, if I ask you, if I talk about that, if we are moving from left to right, is the covalency increases or decreases? If we are moving from left to right, the covalency increases or decreases? If we are talking in the second period, from left to right, if we are moving from here, okay, the covalency increases or decreases? This is the carbon line, okay, carbon one. This is the second period, carbon there. So we say that the covalency increases, okay, and then after this one covalency decreases. Okay, after this one covalency decreases. How I can say that? You can simply know this one very easily. So if I know here, this is helium, hydrogen, helium, then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay, and then neon. So you know this is going to have +1, +2, +3, +4, and then -3, -2, -1. So since the valency is decreasing here, and for up to the carbon it increases, and then after the carbon it decreases. Okay, understood? But in the third period it is not so. But if we talk about in third period, okay, if we are moving from left to right, we will say that the covalency keep on increases. Okay, increases as we move from left to right. And this which one is it? Like we have sodium, magnesium, okay, then aluminium, then silicon, then we have phosphorus, then sulfur, maximum covalency is 6, and then chlorine, maximum is 7, and then after this one. So we are just, as we are moving, we know that chlorine have Cl minus, it has -1 valency, but it can show in excited state, it can have maximum 7 unpaired electrons. So we can say that because it is going to have d orbitals, and because of d orbital, the maximum unpaired electrons a chlorine can have is 7. So it can make bond with 7. Okay, understood? So covalency directly here, we can say that covalency don't increase, decreases. First increases and then decreases. Like in the second period, it does not happen in the third period. Okay. Okay. You're not replying. Noha, Suhail, speak something.
Yes.
Okay. Have you noted this one? Have you noted?
Yes.
Okay. So if I talked about this one, the existence of species. that that how these species exist and how it is possible to exist this type of species. Okay, so let's talk about this one, existence of species. Of species on the basis of their covalency. Okay, so if I'm having BH4 negative molecule, BH4 negative molecule, tell me, is it possible that the BH4 negative molecule can exist? Can it exist? So let's check. Let's check the electronic configuration of the central atom. This is boron, okay, and it is going to have electronic configuration 1s2, 2s2, okay, and then 2p1. Okay, now this is going to have 2 electrons here and 1 2 and 1 electron here in the ground state, but when it is in excited state, it is going to have this one. Okay, understood? Understood?
Yes.
So when one hydrogen atom come, it is going to have a structure like this, BH3, and one H negative ion, which is going to have its own negative charge, means it is going to have 2 electrons. When it comes, it is going to make bonds, coordinate bond here. And now this H negative ion is going to use its own electron, because boron has 3 electrons in its outermost shell, 2,3. It has utilized its 3 electrons here. But let's check this. This is one hydrogen atom electron. I'm writing here. This is one hydrogen electron. It is coming here. This is another hydrogen electron. It is coming here. This is another hydrogen electron. It is coming here. But you see that there is a one vacant space is there, which a boron can have filled with 2 electrons. So this 2 electron, which is going to have H negative ion, is going to carry. So this H negative means both of the 2 electrons of H negative is being carried with this boron. And these 2 electrons are coming here and then making bond with this one. Okay, so here, so we can say that since the space is available with boron, so BH4 negative ion is possible. So we can say that BH4 negative ion can exist. Okay, understood? Understood?
Yes, sir.
Yes.
So let's check CCl6 minus 2. Can it exist? CCl6 minus 2. CCl6 minus 2. Is it possible that CCl minus 6 can exist?
No, sir.
No? Yes, it cannot exist. Why it cannot exist? Let me help you. That this is carbon. This is going to have electronic configuration 1s2, 2s2, 2p2. Okay. So 2,4. Yes, 2,4 here. So this is going to have 2 electrons here, and since carbon is of second group, okay, it cannot have covalency more than 4. Okay. So here it is going to have this 2 unpaired electrons. But when this is going to, when carbon comes in excited state, this second shell from 2s2 and 2p, this will jump to this one and will form this one. Now it has 4 unpaired electrons. So it can form CCl4. 4 electrons from chlorine will come. 1 chlorine atoms will come here, and we can make bond with this one. But the other, for the 2 chlorine negative ions, is not, there is no space here. So we can say that this molecule is not possible. Only carbon can make bond with 4. It is not possible to hold extra one. Okay. Understood? Understood?
Yes.
Yes.
Check AlF6 minus 3 is possible or not? AlF6 minus 3 is it possible or not? AlF6 minus 3 means AlF3 is simple possible because aluminum can make bond with 3. AlF3 is simple possible. 3 electrons aluminum can make bond like AlCl3. But can it be possible to have extra 3 fluoride ion that is going to have 1 negative charge? Is it possible? Means 2 electrons of this one, 2 electron for this one, 2 electron for this one. Okay, is it possible to have 3 vacant orbital are there or not? Check 3 vacant orbital are there or not. So you know that in aluminium, we have d orbital. That is 1s2, 2s2, 2p6, 3s2, 3p1. So this is the, and d orbital is also there because the first shell is made up of only s. The second shell is made up of s and p. The third shell is made up of s, p and d, where d is going to have 0 right now in the ground state of aluminium. Okay, understood?
Yes.
Now what is going to happen here? We have the third shell. This is going to have 2. This is p and this is d. 1, 2, 3, 4. Okay. Now this is going to have, this is the aluminium electronic configuration 3s2 and 3p1. Okay, the 13 electrons. Okay. Now if this electron will jump to this one, it is going to make bond like this. And these are 3 unpaired electrons, which AlCl3 means 3 chlorine, 1 chlorine atoms. Al is there, 1 chlorine atoms, another chlorine atoms, another chlorine atoms. Okay, so their electrons are participating here. The two electron for this one, 2 electron for this one, and 2 electron for this one, they are participating. Okay, but if another chlorine atoms come with negative charge, and it is going to have chlorine minus means it is going to have completely filled shell. So here these 2 electrons are going to make coordinate bond like this. Another chlorine atom, so they can come here. They can come here. They can come here. So it is possible to, because chlorine, it is going to have, means AlCl3 is going to have vacant orbital. So because of this vacant orbital, it is possible to have aluminum can exist with -3, 3. Okay, so AlCl6 -3 is possible. Okay, understood?
Yes.
Understood?
Yes.
So we will discuss this one in the next class. Okay, so that's all for today. We're going to discuss this one in the next class, dear students. Okay, hope you enjoyed the class. We'll have this class, continue this class the next time. Okay, so that you have studied today, that is the types of coordinate bonds, covalent bond, and you have studied the covalent character. You have studied the role of ionic potential. Okay, and the role of ionic characters and how does it increases or decreases down the group if we are moving from left to right along the period, then how it is being affected. So that's we have studied in the today's class. So in the next class we're going to study the type of molecule this we are studying right now. Okay, and then we're going to study the which, if there is some molecule that can exist, there is a possibility that their electrons they're going to have means they are going to have a space for this, like they have going to have a space, but still their formations are not possible. There are certain reasons. For example, SCl6 is not possible, whether it is going to have a